Member of the Chicago Council on Science and Technology. It's my pleasure to welcome you this evening to this really interesting event. But first I'd like to give you just a little background on the Chicago Council on Science and Technology, or C2ST as we call it. This organization started about 10 years ago, and the object is really to interest the public in developing a deeper understanding of science and technology, in particular to better make informed decisions about careers, about voting, to appreciate and see the beauty and the power of science and technology. The main business of the Council on Science and Technology is to organize events like this. And they have, over this 10 years, hosted about 140 public programs on a very wide range of subjects, such as cybersecurity, Alzheimer's research and treatment, clean energy, global warming, the physics of baseball. I've heard many really interesting talks on cosmology, one of my particular favorites. Artificial intelligence, and others. And all of these programs are offered by leaders in the field. So what I would like to do before we get to tonight's event is just mention a few upcoming events being sponsored by C2ST. On March 31st, we'll be partnering with the Association for Women in Science in an event for their Women in STEM National Summit. On April 9th, Dr. Lisa Elliott will talk about her research on brain development in children. And on May 17th, we'll resume our speakeasy in its regular schedule. So if you're interested in any of these events, in particular what the speakeasy is, you might consider joining. You could do this by talking to any of the people here that you see with these name tags on, or by going online. So getting to tonight's event, this is presented in partnership with the Chicago chapter of the Society for Neuroscience of America. The Chicago chapter, the president of the Chicago chapter is Dorothy Kozlowski, who is also a faculty member here at DePaul. She's not able to be here, but she's represented by Dr. Sandy Virtue, who's a faculty member in psychology. And it's really appropriate that we're hosting this event tonight because they have just recently had approved a brand new BS in neuroscience at DePaul. Applications for fall are now being accepted. So it's a very exciting time for us. All right, so now turning to the program tonight. I'm going to turn this over to our moderator, Dr. Tom Masick, who is Senior Director and Global Program Leader of the CNS Therapeutic Area Unit at Takeda Development Center Americas. For the last 16 years, his primary focus has been the clinical development of new medications for the treatment of psychiatric and neurological disorders. Prior to joining Takeda, he was Director of Clinical Neurosciences at Pfizer. So, Dr. Masick.
Thank you. It's a real honor and pleasure to be here and serve as moderator for this important event. Addiction is not one of my specialties, so I have an equal interest as the audience in learning more about the topic. What I do know about addiction, though, through my other work, is that it affects all aspects of life across all cultures. We know that it's a very complex neurobiological processes that underlie. Sorry, I'm sorry. It's the underpinnings, the neurobiology of addiction are very complex, are related to social cues, learned behaviors, and other things. What we also, when we think about addiction, is there are other relationships to poverty, homelessness, violence, crime, as well as poor performance at work. And in itself, addiction and substance abuse are also closely intertwined with a number of psychiatric disorders, such as anxiety disorders and post-traumatic stress disorder, high incidences of substance abuse and addiction in patients with schizophrenia, bipolar disorder, and depression. And what we know as someone who is involved in the development of new medications, the treatments as they stand now have, there's a lot of room to grow. And hopefully in the future we'll have even better pharmacological and other interventional treatments for the use of, for the treatment of addiction. So our speakers tonight are Amy Lasek, who is an assistant professor in the departments of psychiatry and anatomy and cell biology at the University of Illinois at Chicago. She studies the neuroscience of alcohol and drug addiction at the molecular and cellular level. Her research aims to identify the specific genes in the brain that regulate addictive behaviors. Dr. Lasek also studies the neurobiology of sex differences to understand why men and women respond differently to drugs, with the goal of using this knowledge as a basis for developing more effective treatments for addiction. Our second speaker is Christopher Holden, who is a visiting professor of clinical psychiatry at the University of Illinois College of Medicine. He works as the director of addiction services in the Department of Psychiatry at the university, and also as the medical director of the Substance Abuse Residential Rehabilitation Treatment Program at the Jesse Brown VA. Dr. Holden is a board certified in general and addiction psychiatry, and he believes in taking an integrated approach to the treatment of psychiatric conditions. Our third speaker is T. Celeste Napier, who is a professor in the departments of pharmacology and psychiatry at Rush University Medical Center and is the director for the Center of Compulsive Behavior and Addiction at Rush University. Dr. Napier has received continuous research support from the National Institutes of Health since 1990. Her scientific interests include the neuroscience of motivational behaviors, including those that regulate healthy decision-making versus those that are associated with drug and behavioral addictions. So I'd like to invite our first speaker, Dr. Lasek, to the podium.
Okay, well, welcome everybody, and thank you for coming tonight. I would like to, thank you. I would like to convince you tonight that addiction is a biological disorder and that it's a disease of the brain. And so I'm going to give you an introduction on some of the things we have learned about the basic science of addiction. And so to begin, I want to just give a quick definition of addiction and alcohol use disorders. So addiction has been defined as a chronically relapsing disorder, and it's characterized by the compulsion to seek and take the drug. It's also defined by a loss of control in limiting intake of the drug. And another really important defining characteristic of addiction is continuing to take the drug despite negative consequences. And so this is really important because, you know, addiction can ruin people's lives and you know, they lose their jobs, they lose their families, and that's a really important aspect of addiction. And another thing that's been very interesting in terms of a characteristic of addiction is the emergence of a negative emotional state that develops when access to the drug is prevented. And so this negative emotional state can last a long time, even beyond the initial withdrawal, the acute physical withdrawal, and this is a very important driver of continued drug use. And so just to get in a little bit to the biology, and what I'm really trying to convince you of is that genetics and environment are both involved in the development and continuation of addiction. So, and these are really, this is sort of a little hierarchy here, that your genes and the environmental influences are what cause addiction. And so genetics and environment both affect brain circuitry, the wiring of the brain, neurons that make up this circuitry in the brain, and molecules that are produced by the neurons. And so, and these things, all of these factors are involved in driving behavior. So this is important. When we think of behavior, behavior is driven by the brain and the biology in the brain. And so I want to just get into the genetics of addiction because a lot of people often ask me about what the genetic contribution is to addiction. And so what we know about the genetics is based on twin studies. And so if you look at identical twins, and you either look at identical twins that have been raised in the same environment versus been separated and raised in different environments, you can look at the factor for genetics because identical twins are genetically identical. And you can also compare that to non-identical twins or fraternal twins and look at what the factors are there. And so what we know is from the twin studies is that addiction is actually highly heritable. And so you can look at basically the probability of developing addiction if you have the same genes versus different genes. And a score of 1 means that it's 100% probability that it's an entirely genetic disorder. And so this is, in some disorders, it's very well defined that maybe one gene can cause the disorder and it's 100%. But when we look at things like complicated things, behavioral and other chronic diseases like addiction, we can see that the heritability is still very high. So this is just a list of the types of addictions and their approximate heritability, so that probability. So for cannabis, for marijuana, the heritability is approximately 0.4. For a behavioral addiction like gambling, it's actually 0.5. For smoking and alcohol addiction, again, they're about 0.5. And then, interestingly, things like opiates and cocaine have an even higher heritability score of 0.7. I was talking about environment. So you see that there's this probability, it's about 0.5, for instance. So what are the other factors that contribute? And that's the environment. And so the environment, a lot of studies have established that early life events are very important in environmental factors in establishing addiction. One of these can be, for instance, maternal psychopathology, so mental illness in the mother that leads to maybe deprivation of care or some other traumatic events in the child's life. Parental alcoholism, which we know, again, that parental alcoholism is going to be a genetic contribution, but also living in an environment where the parents are alcoholic are going to lead to increased risk for developing addiction. Also parental rejection, and then physical and sexual abuse as children. And then this has been very well established that people with abuse as children have a higher risk for becoming addicted to drugs and alcohol later in life. And again, there are also later life events that are involved. So, maybe stress in your life, traumatic events that happen as an adult that also can lead to addiction. I've just discussed sort of these things as almost like separate events, but in fact, addiction is really characterized by the combination of your genes and your environment. And so we call this a gene by environment interaction in the scientific terms. And what this means is that the effect of the environment on a disease depends on the genetic makeup of an individual. So this is sort of the genetic makeup you can think of as maybe your inherent vulnerability because of your genes for developing addiction. And then if you have an environmental stressor, that can then lead to increasing that risk for developing addiction. And it's important to realize that also the age of onset is very important. So people who start doing drugs and drinking earlier during adolescence have a much higher risk of really having problems with drug and alcohol later in life as adults. And there are other factors, for instance, the availability of the drug. There's sort of emotional and social support, peer influences, and then the socioeconomic status, as Tom was talking about, the poverty and these sort of factors that lead to drug addiction. And so I thought actually I would give an example of genes that are involved in addiction, because when we talk about genes, we sort of just throw around this hazy term like, oh, your genes can cause you to become addicted to drugs of abuse. So what are these genes? And we certainly don't know everything there is to know about the genetic contribution. There are many studies that are ongoing right now to try to find genes. And I want to highlight that there are many genes involved in these types of complicated psychiatric disorders. But I thought I'd give you just 2 examples just to give you something to kind of latch on to. It's like, oh, okay, that's a gene, and this is why it's maybe involved in addiction. So one of the genes that's been very well characterized, or 2 actually, that have been very well characterized for addiction are what are called ADH1B and ALDH2. And so these are alcohol dehydrogenase 1B and aldehyde dehydrogenase 2. And these are enzymes that are involved in the metabolism of alcohol, of ethanol. And so what happens is that there are different mutations in these genes in different populations of people. And people with certain mutations in these genes have an accumulation of acetaldehyde in the body during the metabolism of alcohol. And this compound actually causes the really unpleasant flushing reaction. And people of Asian ancestry may be familiar with this because they have a higher rate of this mutation that causes this reaction. And so a lot of times they're actually protected from becoming alcoholics because they have such a terrible reaction to the alcohol. And so there is a drug out there, and it's a very old drug, and there's not very good compliance because it makes people feel sick when they drink alcohol, but it's called antabuse. And this drug is basically based on the same idea of this genetic mutations, that you get accumulation of this toxic substance in your body that makes you feel sick. But these are very well characterized as genes that are somehow involved in the development of alcoholism. The other gene that I want to talk about is corticotropin-releasing hormone receptor 1, or CRHR1. So this gene is actually, I like it because it's an example of a gene-by-environment interaction. So people who have mutations in this gene have a higher risk of developing alcoholism. But in addition, if you have an early life stress and the mutation, you have a much higher propensity to have heavy drinking and alcohol dependence. And so I thought that was a good one to illustrate the concept of the genes and the environment. So I thought I'd just dig into the brain a little bit and talk about brain regions that are involved in addiction. And there's a sort of theoretical construct that's out there that was developed by George Koob and Nora Volkow. And this basically breaks down different behaviors related to addiction into 3 cycles. And so the first is the binge intoxication stage. So this is the stage where you feel good, you're drinking or you're doing drugs, you feel really good, you're getting the high. The second stage is after you stop taking the drugs, you go through withdrawal or a negative affect, which is basically the development of anxiety, irritability, depression during withdrawal. And this we can just simply say is feeling bad. And then there's this third stage of addiction that is known as a preoccupation or anticipation stage. This is sort of after the withdrawal, as basically the acute withdrawal is gone, but there's a sort of longer abstinence, and this is known as craving. And this is when people are really wanting to go out and have the drug, and then it sort of resets the cycle all over again into the binge intoxication stage. And so each of these three stages has been studied in animals and in people, and look at basically like where in the brain are these types of behaviors located. And I just wanted to bring this up because I don't know if people are really aware, but there are different receptors that bind to drugs of abuse in the brain. And so for the opiates, they bind to the opiate receptors in the brain. And actually, there are natural opiates in your body that are produced by the brain known as endorphins. In addition, there's delta-9 THC, which is the active psychoactive component in marijuana. This binds to what's known as cannabinoid receptors in the brain. And these are, actually, there are also natural cannabinoids in your brain known as the endocannabinoids. Nicotine binds to the nicotinic acetylcholine receptors. And then cocaine and amphetamine act to block the dopamine transporter. I'll get a little bit more into dopamine in the next couple of slides, but dopamine is thought of as sort of a part of the reward system, or a molecule, a neurotransmitter that's involved in motivation and reinforcement. So these drugs block the transporter, and this increases dopamine at the synapse. And finally, ethanol, which alcohol, has many target sites, but it has very large effects on the GABA system, which is another neurotransmitter, an inhibitory neurotransmitter in the brain. So I just wanted to put that out there. But having said that, the primary effects of drugs, they act on these receptors, but one thing they have in common is that all of the drugs of abuse have primary reinforcing effects by increasing dopamine levels. And so this brings us into the reward system and that sort of brain's regions that we think of are being involved in the binge intoxication stage of the addiction cycle. And so in the reward system, there are neurons in a brain region that's deep in the midbrain, so it's not shown here, known as the ventral tegmental area. And these neurons produce dopamine, and they send projections or axons to other brain regions known as the nucleus accumbens, the prefrontal cortex, or the amygdala, and a few other brain regions. And what happens is these neurons will release dopamine in those brain regions, and that's very important for the reinforcing actions of drugs. So that's what's giving people what's thought of as that sort of motivation, the high, and what we call reward generally, although we try to sort of avoid that term because it's a little bit vague. But anyway, so you can see here that these regions in blue are those regions involved in that binge intoxication stage. The VS here is the ventral striatum, which is the nucleus accumbens, which is very important. But there are other brain regions involved in this, what's thought of as the reward system. Okay, so that's sort of that early binge intoxication stage. But what happens after chronic drug use? And there are neuroadaptations that occur after chronic drug use. So repeated drug use changes brain circuitry and neuronal function. And these changes are thought to be what's involved in relapse and the loss of control over drug taking. And so I wanted now to go into the next stages that we were talking about, the other, there are 3 stages. So it appears that these neuroadaptations are really key for the other stages. So for instance, in the withdrawal negative affect stage, people develop anxiety and irritability and depression, and also decreased motivation for non-drug related activities. So they just don't get the same pleasure anymore from natural rewards like food or exercise or things that make us feel good. And so basically, this stage is thought to be housed in a part of the brain involved in emotional processing and stress responses. And so This is the amygdala here, and then again the ventral striatum, which is involved in the reward system, also plays some role in this stress response. So changes in the brain stress system occur after chronic drug and alcohol use. And what happens is in the amygdala, there's basically a hypersensitivity. There's an increased expression of these stress molecules. And this is the emotional center of the brain. And so this leads to these sort of negative feelings that can drive continued drug use. And this has been very well studied for chronic alcohol abuse. And so actually, I thought this was pretty insightful. I was at a bar, and I saw this sign up on the bar. And it sort of really kind of highlights, I'm not an alcoholic. I'm just a soberophobic. I mean, why would I want to be sober when it makes me feel like this? So anyway, but somebody really was in tune with the science in that bar, I think. So the third stage that I was talking about is that preoccupation anticipation stage. So this is also known as the craving stage. And this is really thought to be also a major factor contributing to relapse. And so this sort of stage of addiction is thought to be housed in the prefrontal cortex, or the frontal cortex of the brain. And these are the areas that are involved in proper decision making. So the medial prefrontal cortex, the anterior cingulate, the orbital frontal cortex, and then also areas of the brain that are involved in memory in the hippocampus. So impaired function in these brain regions has been found in using imaging studies in people with addiction. And so because of this impaired functioning, it's thought that these areas, that this actually leads to the inability to make good decisions and prevent person from continuing to use drugs despite the negative consequences. And so basically that was my little intro to neuroscience of addiction for you, and we'll move on to the next speaker, who is Chris Holden. But I hope that I've convinced you that addiction is a biologically driven disorder, and that it's all contributed by genes and environment, and how these things can change the brain and lead to behaviors that lead to addiction. And also, because we know that it's a biologically driven disorder, we can think about how we can manipulate that, the circuitry in the brain and some of the molecules, to find new therapies to help people with addiction. Okay.
Is it on?
Yes.
Sounds like it. Is there a timer or anything? I'll figure it out. It has a timer. A timer. I'm going to periodically look up there just to see how I'm doing for time. That's what that is. It's not a twitch. The twitch will be something different. Anyway, so just to get started, to touch a little bit on the scope of the problem, which I think everyone has at least a broad understanding of. It's drugs and alcohol, when you include tobacco, is a huge problem. It contributes to over 500,000 deaths a year, just enormous amounts of financial destruction wrought. And it also, we've had many epidemics related to drugs over the years. Most recently, we're in the midst of a prescription opioid epidemic. Just to not necessarily cherry pick, but just some examples. This is a statistic that gets bandied about. So what this is, this blue line, and this slide is made by the CDC. This blue line is motor vehicle accidents that have occurred, or people that have died from motor vehicle accident, starting here and working their way down. So, things are getting better and better as years go on. And then this green line is overdose deaths or deaths by poisoning. And then the red line basically is deaths by overdose, not just poisoning per se, like, drinking bleach or whatever, but an actual like drug overdose. So around this time, basically at this point in time, more people began to die from drug overdoses than motor vehicle accidents. And if you break this down, the overwhelming majority, at least at that point, was due to prescription overdoses. So, and then it gets worse. In 2014, there have been more deaths by drug overdose than ever before in the history of the United States. In fact, 50% more people die from drug overdoses than gun violence and motor vehicle accidents. And the majority of this is opiates, prescription opioids, and now heroin, but other things as well. But those are the big ones. So throughout history, addiction's been primarily viewed from a moral perspective. The idea being that the basis of addiction is moral failing, a lack of willpower, somebody being bad or evil, and what have you. And it's been, like I said, it's been the only model for most of history. Not only that, it's still the dominant model in the public, healthcare providers, the government, and so forth. The reason why I think is because it makes sense. It makes kind of intuitive sense when you're faced with somebody like a family member or someone you see on the street or a patient with an addiction, and they're behaving the way they do. They're lying, they're stealing, they continue to do something, and it seems like they're doing it, for reasons to get high. It makes sense that it would be, that it's some sort of moral failing. And then there's implications that come with this. One is someone who is a moral failure, you don't treat that per se. Rather, what you do is you punish it. You blame them. And this is where the criminal justice system comes in, and so forth. So there's other models as well. The one we're talking about primarily today is the disease model, but there's other things as well, such as the idea that people self-medicate, the idea that addiction is that it's all environmental and what have you, and different models basically all have their own sort of usefulness, but just we'll be focusing on the disease model. And the idea behind the disease model is that addiction is not a moral failing, but rather it's a disease. This concept has been around for a long time. When Alcoholics Anonymous was founded in the 1930s, alcoholism was actually described as a physical, mental, and spiritual disease. Not only that, but in the 1950s, the American Medical Association recognized alcoholism as a disease. In the 1960s, research started to show that methadone was effective in the treatment of heroin use disorder in the face of the heroin epidemic, and so forth. But acceptance has been partial. Even though there's been all of this that's occurred, it's, again, the moral model still predominates. And treatment hasn't really caught up to this. Moreover, we still take a very kind of punishing, criminal justice view of addiction as well. And so one of the reasons that we think that this has been a problem, or this hasn't really caught on, is because the scientific underpinnings up until this point have been lacking. So this quote I have here was originally was a different quote. I saw this quote of this ancient Japanese proverb that was first the man takes a drink, then the drink takes a drink, and then the drink takes the man. And I thought that was very powerful, and I saw it mentioned a couple different places, but then I decided to Google it. And it turns out I think that quote was made up, and that it actually, F. Scott Fitzgerald made this quote, and then somebody reverse engineered it into an ancient Japanese proverb. So, but just pretend it, like, because the man has more potency than you. The idea that, like, first somebody takes a drink, and then eventually the drink kind of takes over, and the drinking is kind of what keeps the drink is what keeps the drinking going, right? To stave off withdrawal and what have you. But then ultimately it causes all these profound changes in what makes somebody who they are. So, yes. So not only is addiction a disease, it's one way to also view it is as a chronic disease, much like other chronic diseases that we have, such as diabetes and high blood pressure and what have you. It's not something that you either just punish or send somebody to detox and basically, a week later they're cured. And if you follow along with this disease, this chronic disease model of addiction, it wouldn't make sense to approach high blood pressure or diabetes or other things like that with the way that we kind of currently approach addiction. For example, it would be like giving somebody, a month's supply of blood pressure medication, or a month's supply of insulin, or yell at them to not have diabetes anymore, and so forth. And you might say, like, and I think what I remember when I first heard this, the thing that would occur to me, but addiction's different. There's this behavioral component to addiction that's not, high blood pressure is something you have. Actually, if you think about it, though, like, that's actually nonsense. These chronic diseases like high blood pressure and diabetes have huge behavioral components. And there's things such as adherence and what have you, and sticking with your program and your diet and taking your medications and what have you, that are problematic for all these things. This is a classic article in the Journal of JAMA, the Journal of the American Medical Association, that looked at relapse rates for different sorts of chronic diseases. And diabetes, type 1 diabetes, not particularly good. About 40% of people relapse. Drug addictions, around 50%, high blood pressure and asthma. So it's right up there. Chronic disease is characterized by relapse or recurrence. So to talk about addiction now, not only as a disease, but as a brain disease. So if addiction is disease, the organ that the addiction affects is first and foremost the brain. So a couple different things happen. Dr. Lasik talked about these, but just to kind of reiterate them and maybe a little bit more, actually just to kind of reiterate them. So I think she essentially said the same thing, that you have the drive, reward, pleasure centers of the brain that are hijacked. These are parts of the brain that are designed for, to kind of compel you to seek out food and to reproduce and to do good things that make you feel good. These get hijacked by these substances that are targeted in a very targeted way affect these areas. And then what also can happen is people's kind of their decision-making circuitry gets affected, so that they have a harder time resisting urges, that the brakes part of the brain, the parts that helps with keeps you from being impulsive, gets affected. The part of the brain that allows you to kind of think about the future and how to plan for things, that gets affected as well. And then not only that, this thing called the anti-reward pathway is thought to turn on. There's this hypothesis and good evidence for it that when you bombard the pleasure center of your brain with these substances over a long period of time, your brain is pretty good at basically saying kind of what's going on and trying to react to it. And what happens is this other system called the anti-reward system kicks in, that actually kind of can put people in this kind of miserable, distress sort of state, independent of actually using the substance, then that can stick around for a long time. Does that make sense? Cool. So then because of brain changes, the person with an addiction is fighting a war on a battlefield stacked against them. I guess you don't have a battlefield stacked, but card game stacked wouldn't have worked so well. So you've got these three different areas. One, there's the decision-making system, right, where people have trouble resisting urges, difficulty making plans and following through. Then you have the stress system, which is the anti-reward system. People are irritable, they're depressed, they're distressed, and they also perceive that the only relief that they can get from this is through substance use. This is one example of, or one way to explain craving. And then there's the reward system that people ordinarily have. It gets diminished. Things that ordinarily give pleasure don't do it like they used to, like doing a good job at work and so forth. And what oftentimes happens is that substances become the only source of pleasure, the only thing that's compelling. All right. And then I just circled pleasure right there because, like, classically, when you think about, or when people think, if you use the moral model of addiction, that's pretty much all it is. That's why people use substances. So we would argue that it's a lot more than that. So addiction's not just withdrawal. Addiction's not just seeking pleasure. There's these long-term changes that can occur that can take a long time to come back. And not only that, even after somebody stops using, these changes can stick around. There's all sorts of different examples of it, but one of the best ones is that there's this long-term study of people starting, I believe, in the 1960s who were heroin addicts, and that they followed them over decades. And there was this most of them are either dead or in prison or actively using, but there was this subset of them that had 15 years of not using. So these are the success cases, right? And it was a small subset of them. But so of these people who were doing well, who had 15 years of doing well, within the next 5 years, a quarter of them relapsed. So, even the risk is always there. Like, you would think, intuitively, these guys are in the clear. They had a horrible problem and they got through it. So, which leads me to talk about pharmacotherapy, starting with opioids. So the classic one is methadone, which has been around since the late 60s. And so you recognize this from Dr. Lassik's talk, where you have these different stages of addiction. There's the intoxication stage, the withdrawal stage, and the craving stage. And one way to think about how methadone works is by using this model. So at relatively low doses, people start methadone, and it prevents them from being in withdrawal. But then what seems to work is people go on higher and higher doses, and you're like, well, why do they need higher doses if a relatively low dose can prevent withdrawal? So what can happen when people get to higher doses is that cravings can be reduced or attenuated. But where the real magic, for lack of a better term, where some of the real kind of remarkable effects of methadone can occur is actually in this stage of the intoxication stage. That if people get to a sufficient dose of methadone, they become tolerant to the effects of opiates that cause, like, euphoria, that are reinforcing and what have you. So if the person uses heroin on top of methadone, nothing happens, and they're able to come to their senses. I forgot to mention what methadone is. Methadone is an opioid. And so all sorts of wonderful things happen when people are on methadone, keeping in mind that the overwhelming majority of people who go into methadone maintenance treatment stay on it for less than a year. People do tend to have a better chance of sticking around in treatment on methadone than are not on methadone. Their medical problems tend to get better. Their psychiatric problems tend to get better. Crime tends to go down. Transmission of HIV and hepatitis C goes down. All sorts of great things happen. So then there's also a medication called buprenorphine, which is similar. So heroin, morphine, opium, methadone, these are all full activators of the opioid receptor, whereas buprenorphine is what's called a partial agonist or partial activator. It's almost like if you imagine a dimmer switch, these other things turn the switch all the way on. Buprenorphine only turns the switch halfway on. So some interesting things occur. You don't get the full effects of an opioid, but this other thing that buprenorphine does that makes it particularly special is it binds that receptor really tightly. So even though it doesn't turn it all the way on, it binds it really tightly. So going back to this, buprenorphine can prevent withdrawal. When people are on it, it can also help with craving. And then it works on the intoxication stage a little bit different in that it binds that receptor so tightly so that if anyone uses a substance on top of it, like heroin, ideally what happens is it basically is like this gatekeeper that keeps the heroin from binding so the person doesn't get the effects of heroin and they're able to come to their senses and using substances become less compelling. There's also naltrexone, which is an opioid blocker so there's agonist or antagonist essentially. The issue with that, so it would primarily work in this area that when people take it, it blocks the effects of opioids. The real issue with that is adherence because it doesn't do anything for withdrawal and craving. So I'm going to move ahead and talk about alcohol. In pharmacotherapy for alcohol, there's a number of different medications that have been FDA approved. There's also several medications that are not FDA approved that have a lot of promising results. So acamprosate is a medication that works in the GABA and glutamate system. Dr. Lasik talked about GABA a little bit earlier, and it seems to help both with kind of the withdrawal state and the craving state. Naltrexone, we talked about just a minute ago, is an opioid blocker. So why would you take it for alcoholism or alcohol use disorder? It appears that the way, or one of the primary ways that alcohol is reinforcing and rewarding and addictive is through this opioid receptor system in your brain. So what they found originally in animal studies is that like if you get rats hooked on alcohol and you give them naltrexone, they stop being hooked on alcohol. So naltrexone appears to primarily work in this stage, but it also seems to help with cravings as well. And then there's disulfiram or antabuse, the idea being that if people drink alcohol when they have that in their system, they become very sick, so the intoxication stage is no longer intoxicating. But the big issue with that is adherence. And so one of the things that's kind of promising right now is that it's thought that different people with different genetic makeups might respond differently to different medications and so forth. So I hate to give tobacco nicotine short shrift, but this is somewhat redundant. So one treatment for nicotine is nicotine replacement therapy, like the patches and what have you. And if you follow out what we've been talking about thus far, it makes sense. Keeps you from being in withdrawal, can help with the cravings. And then varenicline or Chantix is this medication that seems to actually work, kind of be the, not to get into too much, but seems to be kind of the nicotine equivalent of buprenorphine. So now to talk about pharmacotherapy for stimulants, namely amphetamines and cocaine, as well as to talk about it for cannabis, there really isn't at this point. But I believe Dr. Napier might. So anyway, sneak preview. So unfortunately, these are something that there isn't good pharmacotherapy for. And then just to touch a little bit about on non-pharmacotherapeutic treatments. There's cognitive behavioral therapy, the idea with various ideas about it where people learn about the disease, they learn to identify triggers and cravings and things like that. There's a style of therapy called motivational interviewing, which starts with the idea that motivation is the basis for change, but that motivation through various interventions by a therapist or treatment provider can actually be enhanced in somebody. And then other things like mutual help organizations like AA, NA, and so forth can really help with the behavioral aspects of change. Just to talk really brief, I'm going to just kind of plow through these, and if people have questions about them in the discussion, feel free to ask. But basically, current addiction treatment is not what it should be. There was a study in 2012 that they did at Columbia University that basically said that addiction medicine is similar to like how general medicine was about 100 years ago, that you could have people from top flight universities providing treatment right next to quacks. I mean, there's still quacks around, and that not only that, but most treatment for addiction is separated from healthcare. It happens outside of hospitals and medical centers and clinics and what have you, and that it tends to be underfunded, and that is primarily given by substance abuse treatment providers, where there just isn't a lot of quality control. There's no mandatory national certification exam. Most states don't even require a bachelor's degree, and there's a really high turnover rate, and not apparently more turnover rate for substance abuse treatment providers than people in the fast food industry. I mean, that's not to say that they don't make heroic efforts and do very good work, but it's right now addiction treatments is kind of a mess. But not only that, healthcare providers are really not doing their jobs as well. Even though we're experts at treating chronic conditions, we don't have training in addiction in our medical schools, and it's the same in nursing schools and pharmacy school and what have you. There's not many doctors who I'd self-identify as being able to treat addiction, and the result is we don't recognize addiction when you're coming to see your doctor, in your doctor's office. We don't know how to treat it. We don't view addiction as a disease. I mean, we're talking, we can give lip service to it and say, hey, addiction is a disease, but I think at the end of the day, the average healthcare provider still primarily adheres to the moral model. And then not only that, we can contribute to addiction, and I think that's one of the things that's happened with the prescription opioid epidemic, that we don't know what's happening right in front of us. So, just to look a little bit at basically, the VA is actually better than the average place in terms of treating addiction. But even so, in the VA, only 3% of veterans with alcohol use disorders are offered medication to treat alcohol. And they looked at why. Apparently, patients don't ask for it. Doctors don't think it works. Doctors don't know how to use it. And they looked at ways to help with that. One is to educate patients. Another is to educate healthcare providers. Another one is more compelling research. So, and things seem to be moving forward. With the Affordable Care Act, there was a mandate that we had to treat the diseases of the mind as well as the body. So there's more money being put into treating addiction, and with that, they want it to be as cost-effective as possible. There seems to be a movement to decriminalize addiction as well. And I don't know if you're kind of hearing about it in the news. I'm kind of attuned to it, so I keep hearing it more. But the White House keeps talking about more and more funding to treat opioid addiction because of the rise in heroin and prescription overdose deaths that we have, including apparently asking for $1 billion in new mandatory funding over the next 2 years. And I'll skip that last bit. That's kind of an aside. Not a great way to end. Anyway, thank you.
Well, thank you all for hanging in there tonight. I think this has been an excellent prelude to the things I want to talk about, which is going to be the excitement of neuroscience. I want us to end on a positive note because I think the future is positive. I think people like you are very important in making sure that we understand this disease called addiction, and that we understand that the stigma is not helping our society or the individual who's afflicted by this disease. And so what I want to do is to expand a little bit on the 2 prior talks that you've already heard tonight, and sort of open the curtain and let you see the kind of research that is moving addiction. Can you hear me? No? Could you move your mic up? I can. Maybe. How's that? Is that better? Good. To sort of give you an insight into how we do medications development to try to find new treatments for this very complex disease called addiction. So one thing, you've heard it already tonight, I want to underscore this, that we truly believe that addiction is treatable. And I think the future is very bright in that regard. And in order for us to be able to do a good job of treating those who suffer from addiction, we really do have to understand the brain science that you've already heard from Dr. Lasix, and a little bit of the neurobiology and the molecular events that occur as the brain communicates within itself, and those brain regions that become disturbed during the process of addiction. So to sort of recap on what you've already heard about tonight, this is a section through the brain. If I look this way, it's like this. The nose is here. Oops, I knew I would be doing this. You saw my surprise. I can't believe I did. So this would be the nose. This is the back of your head. This is cutting through the middle. And the different colors are sort of representing some key structures you've already heard about tonight. You've heard about the prefrontal cortex, the orbital frontal cortex. These are the parts of the front of the brain that we're really proud of as humans. We think we're really smart. We've got a big one. And that's what helps us make decisions. It's where very complex behaviors sort of reside. Down deep in the brain is these brain regions called the nucleus accumbens, and its output, the ventral pallidum. I always put the ventral pallidum there because that's my favorite brain region, and so it's going to be yours as well. But these brain regions are very important in reward, as you heard about tonight, and salience. And what that means is that these are the brain regions that sort of attribute significance to something. So if I eat a brownie and I really like it, which I do, brownies are significant to me. All right? And that's because my ventral pallidum is attributing salience to that chocolate. You've already heard about the amygdala and hippocampus as well. These brain regions are very much involved in learning and memory. You've heard about the amygdala being important in stress, and that's because the amygdala is very important in emotional memories. So when I eat my brownie, I'm very, very happy. I have a happy memory of brownies. That's my amygdala. Right? So how does this all work together to make a decision to do something, like, for example, to take a drug or not take a drug? And this is a diagram for you here on your right. So if something feels good or it's salient, your dopamine system, which is, you've already talked about, is very important in regulating rewards in this, for example, nucleus accumbens. And the nucleus accumbens then talks to this orbital frontal cortex, and it says, this is really good. I really like it, right? And then we have maybe this memory of doing something before. I liked that brownie before. I had it again. I remember I like it again. My hippocampus and my amygdala is telling me it's good. The amygdala says it makes me happy. It talks to this reward center to remind it that it makes you feel pleasure and good. And that's telling your cortex again where you're making a decision, that orbital frontal cortex, for example. And it's sort of biasing your decision towards doing something like eating the brownie. Now, up here is this thing called control. That's being modulated, if you will, by the prefrontal cortex, and we call this inhibitory control. And that's sort of like if you have the devil and angel on your shoulder, and your orbital frontal cortex is saying, do it, do it, do it, do it, do it. And the medial prefrontal cortex is saying, let's wait. Let's think about it a little bit. Maybe if we didn't eat the brownie, we wouldn't weigh 400 pounds. And so this is the decision conundrum that goes on in our heads all the time. But you see, you're getting input from your emotional memories and from your pleasure center. And what happens if these things are working full tilt, your decision is going to be do it, do it, do it, do it, do it, right? And that's how we make decisions. So what happens during addiction, as you've already heard a little bit about, is these brain regions that have to do with pleasure become hijacked, if you will, by the very drugs that the person is taking. This becomes very big. And what happens is the part of the brain that's over here in terms of inhibitory control is not working so well. It goes offline. So then you can see this trifecta that's happening here. It feels good, I remember it, I want it, I go, I choose, but I choose the drug. So this is the circuit that we know is very much involved in this process that develops that we call addiction. And what I study is to look at some of the things that regulate these systems, especially those parts that have to do with learning to become addicted, Interesting thought. And how that might contribute to craving. I remember it, I want it. And then how that might make it very difficult for someone to stop taking the drugs, and thus may contribute to relapse. And that's what we're going to talk about in the next few minutes. So, what are these memories and addiction? It's all about people, places, and things. All right, you all know this. We go to our bar that we like, and we get our favorite drink. If I have a margarita in a Mexican bar, the possibility is I'll go back to that place again. And what happens then is that you start to associate that bar with the feel-good memories of that margarita. Are you with me here? So if I had a really bad day at work and I walk down the street and I'm heading towards that door to that bar, I'm feeling better already. I don't even have that margarita yet. And that's because we've learned to associate, for example, the bar, that context, with the feeling good that we get from the alcohol that's in the margarita. And we learn this. And guess what? Marketers, people who are in marketing, know that too. What is this? Everybody knows what this is. It's coffee. Even though I've blanked out the word coffee, you probably didn't even notice it wasn't there, right? Because you saw this green and this goofy mermaid. I've never understood that mermaid. But you know it's coffee. And I can clue you, if you see this sign in O'Hare Airport, what are you doing? You are running towards that sign and you're buying that coffee before you get on that plane. That's because you've associated this logo with the feel-good that you get from the caffeine that's in your coffee. All right? So we all do this every day to some extent. But what I want to talk about is if this kind of emotional memory and this salience, this importance has now been attributed to a drug, can we break this link? As a neuroscientist, if I understand how this occurs, can I break that link and dissociate that bar context from the feeling that one would get from the alcohol, so that the alcoholic could someday walk into a bar and not crave to get a drink? That is my hope, and that's the kind of research that we're engaged in here. So here's an example about the biology of craving. And this was a study, it's a pioneering study done by one of my friends, Anna Rose Childers, back in 1999. And what she did is she took recovering cocaine addicts and she put them into a brain scanner, and she showed them one of two videos. One video was this lovely stream with birds and butterflies and mountains and, who knows, kittens and dogs, I don't know. Some neutral, lovely, lovely screen, movie. And she asked them, how are you feeling? Oh, they're fine. I'm fine. I'm fine. But if she shows them a video that is of things you use when you take cocaine, a white line of powder, a credit card used to cut it, for example, then she would ask these recovering addicts, how do you feel? And it doesn't surprise anybody that they say, I'm craving cocaine. And all they saw was a video of paraphernalia that's associated with the taking of the drug cocaine. And then what Dr. Childress did is she actually scanned their brain, and that's what you're seeing here. And in this case, what you're looking at is the brain is cut like this. It's called a horizontal section, and it's turned up. So this now is the nose, and this is the back of the head. And what she saw, in contrast to when those cocaine addicts who were now recovering were looking at neutral videos, she saw this frontal cortex light up. Red means more activity, occurring when these individuals were looking at the video that contained paraphernalia associated with cocaine taking. What that means is this brain region is hyperactive. And we now know that part of this has to do with the difficulty in making proper choices when you're craving a drug. Your brain is in a different state. Your capacity to make a healthy choice is indeed compromised, and we know the biology of this. All right, so now that we know from human studies, and we know from behavior as well as looking inside the human brain with our modern technology, that we can understand the changes in the brain during the addicted process. What I want to do is talk about some examples of how neuroscience then is helping us develop new treatments for these changes in the brain. All right? And again, I'm into anti-craving compounds. I don't want one for brownies, but I will think about other types. So in terms of anti-craving, again, for us to be able to reach this lofty goal, we really do have to understand the neurobiology of craving, which is pretty wild when you think about that, right? But we know enough today that what happens in the brain when you're going through craving involves many of the same neurotransmitter systems that have been altered during the process of taking drugs. And as a pharmacologist, I believe we can insert pharmacotherapy or treatments that can then rectify this imbalance. For example, you saw this hyperactivity in the frontal cortex in those cocaine abusing individuals who are craving. We can help restore balance. We may not be able to cure addiction, but we can compensate for it, I believe, such that the people who are afflicted with this disease can lead normal and happy lives. So, what do? I don't work with humans, I work with rats. So now I have to convince you that rats can tell us something about humans. Now, before I say this, I want you to know, me and all the people in my lab are animal lovers. We have dogs, we have horses, we have cats, some of us have pet rats. And we take very good care of our animals because happy animals and healthy animals are the ones who are going to give us appropriate data in terms of biologically relevant data, plus the fact that we know that it's very important to be kind and respectful of these animals because we are doing research on them. And the other reason this is relevant is shown here. The big thing there is a human brain. And of course, your brain is about the size of your two fists fitting inside of your head. And this is looking at one side of that fist. And again, this would be your nose, and this is the spinal cord, this is the back of your head. This is a brain of a cat, a relatively small cat. And this is a brain of a rat, and that's a big rat. That's a pretty big brain. But that's just to show you size differences. What's more relevant to our conversation here is that we know that parts that are in the human brain that are important, this is just showing you one that's sort of part of the cortex called the motor cortex, is represented in a cat and in a rat. And even though they're in different places and they look different, the functions are similar enough that is perfectly appropriate and very informative to use these silly little animals, mice and rats, to provide incredible information about how the human brain functions. And Dr. Holden has already mentioned an example of experiments that were done in rats that proved to be absolutely a total parallel with human work such that it helped to develop a new treatment for human addiction. And that's what we're doing in my lab as well. To make this point even stronger, a couple of years ago, I co-authored a paper with one of my friends, Harriet DeWitt, who's a professor of psychiatry at the University of Chicago. Amy Harold is a brilliant student in my lab who's now at the Heinz VA Hospital, a wonderful woman. And we wrote this paper to make this point. And what you'll see here, for example, one of the drugs that Dr. Holden talked to you about was varenicline or Chantix. The point of this paper was that we could show the experiments in rats done with one paradigm called condition-place preference, and we're going to talk about that in a minute, that predicted clinical utility of that very compound in a human. And varenicline was one that you've heard about. Naltrexone is another that we talked about in this review. And so what I'm going to do is expand tonight on the two drugs that we use as examples that we think are going to be in the pipeline that will be useful in the future. One is mirtazapine, which is an antidepressant that we think should be repurposed for the use of addiction therapy. And another is baclofen, which influences GABA transmission, which you've already heard about tonight as well. So that's what we're going to talk about. One is new things that are happening. Two, that we can study rats and we think that they're going to be appropriate in humans. And if you're interested, this is a very cool review because it talks about you could do condition-place preference in humans and condition-place preference in rats, and they do the same thing. So you think that's special? It's just like the rat. Now, so what is condition-place preference? All right, we already talked about the idea of going to a place, the bar or the Mexican restaurant, and you learn to associate that place with the feel-good of a drug. In other words, you've conditioned your brain to prefer that place. And that's what we're doing in these animals. For this paradigm, basically what we do is we have two sides of a box. And let's say, for example, this side is going to be like the bar, and this side is going to be like at home when you have to do homework or taxes. How's that? So we put rats in here and we let them run around and we sort of see that they don't really care where they are. And what you notice is that one side of the box has the different visual cues on the wall. The floors feel different. So that way they can distinguish one side of the box from the other. Then the next phase, what we do is that we put a little wall here. And on one side of the box, we give the animals salt water, which is like saline, which should have no feeling whatsoever. And on the other side of the box, on a separate day, we then give the animals some drug, like, for example, methamphetamine or cocaine or heroin. It doesn't matter the drug. It all works the same in this particular paradigm. And after a while, they start to associate these cues with meth, just like I would associate the cues of a bar with beer. And they would associate these cues with boring, nothing, right? So after they've learned to associate that context or that environment, their brain has changed. They've learned, right? They've learned to take this feel good and make it relevant to that place, the beer and the bar. What we do on the test day then is we put that rat in here, we take away the walls, and we say, show us where you want to be today. Well, if it's me, I'm in the bar, right? If it's a rat, he's on this side of the box. So in the paradigm called conditioned place preference, and Dr. DeWitt has done this in humans, in rooms at University of Chicago, and humans do the same thing. Same thing. It's amazing. What we can do is just look at the time that the animal spends here versus here, even though they don't have any drug at all. And we can determine if they've learned the feel good is associated with this place. And then we can look at how their brain is changed. And that's what we do. And it looks like this. Time spent in the meth paired side of the box is much greater than the time spent in the side of the box that previously was paired with giving them saline or salt water. All right? Your brain has changed. You've learned to associate this place with the feeling good of the drug, and it's so powerful that you don't even have to have the drug on board in your brain for you to want to go back to that place, and you're going to feel good already. Well, we can take this paradigm then and do a lot of things to study behavior. One of them is called extinction. And extinction means, it's sort of like if you have a phobia. One of the ways one might consider getting over it is to expose yourself to that thing that you hate until it becomes a little less spooky for you. You extinguish that fear. Well, what we do for the rats is we play a little joke on them. We put them in here over and over and over again with no drug. Or we put them in this side, which they normally got methamphetamine, and this time we give them saline. So eventually the animals extinguish that behavior, right? That means that that brain has relearned something new. I no longer get my favorite drug when I go here, okay? But what we now know as scientists is that the animals never totally forget that they once in their life got methamphetamine on this side of the box. Because if you give them methamphetamine and then you put them in the box and say, how do you feel? Show me by going to the side of the box where you previously felt that same way, and that would be the methamphetamine paired side. So after you extinguish the animal, we know, as in humans, that these rats still have a memory of that methamphetamine. And so even though they may act normal, if you trigger them a little bit with just a little bit of methamphetamine, zip, right over they go. Just like if you have one little drink, you might go right back to that bar because your brain still has the memory of those drugs. And we can demonstrate that in the animals. So we can use this paradigm then to say, one, can we help move this extinction training further along, or can we even make it so profound that the animal really doesn't want to feel that methamphetamine anymore? And this was one of the questions that one of my graduate students, Robin Voigt, tested using condition-place preference. And in this case, she gave the drug baclofen, and this is the GABA affecting drug. It actually acts on a specific receptor for GABA called GABA B. It's used, it's already used in humans as an antispasmodic, so we know it's safe. And so we hypothesized that GABA should break this link between the place where they got the methamphetamine and the feel-good of methamphetamine, and she tested that, and sure enough, she was right. Now this looks complicated, but it's really cool, so bear with me. So we train the animals, put them on the meth side box, put them in the saline side of the box, meth side box, saline, meth. Robin worked very hard. You see how many days this took for these animals. But on the 9th day, we put them in the box and let the rat run around and say, where do you want to be? And where do they want to be? They want to be on the meth paired side, where they got that methamphetamine. That doesn't surprise anybody, right? And we had 2 groups of rats. Here's one group, here's another group. Both groups of rats did the same thing. They want to be where the methamphetamine used to be, right? Well, then we wait 40 days. And these rats live about 2 years. 40 days is a long time to be withdrawn from their methamphetamine. They only got it 4 or 5 times, right? They only got it 3 times in this study. 3 doses of methamphetamine. And during that time, we were trying to extinguish the animals. We put them in that box and they didn't get meth, but we gave them baclofen. And what we found, which was totally cool, was that if they got the salt water, saline, or what's called the vehicle here, they still remembered all these days later when they got tested again. It's amazing. These rats felt meth 3 times, and they still remembered that context. But if you give them baclofen, look at what happens. They don't care anymore. It's absolutely remarkable that we completely broke the link that they had learned to associate a place with the methamphetamine feeling. So we think this is a really important drug that we're trying to explore in humans to see if we can help a psychiatrist, like Dr. Holden, to increase the rate and the strength at which we can extinguish the need to feel the way these drugs make you feel. We're quite excited about this. Another study has to do with a drug called mirtazapine. Mirtazapine is an atypical antidepressant, and we think it has the pharmacological profile that makes it very useful for trying to stop methamphetamine and cocaine addiction. As Dr. Holden told you, there are no treatments right now for methamphetamine and cocaine and amphetamine, so we're very interested in doing so and trying to find one. This is Steve Graves, who's a previous student in my lab. He's now at Northwestern, doing his postdoctoral residency there. And what he studied was looking at another paradigm to expose the animals to methamphetamine. In this case, the animals got to give the drugs to themselves. And yes, rats can self-administer a drug just like humans. But the way we let the animals do that is that we surgically implant the animals with an IV catheter, just like humans or your pets. You might have had a pet who's been very sick. Like if you're trying to give cancer chemotherapy, you have a port. That's what we do for these animals. We use the same procedures that you would in a veterinary office. And we teach them to press a lever to get methamphetamine. The other lever here, they only get saline. So they learn where to go to get the drug that they are interested in. And whenever they press methamphetamine, a light comes on. So what do you think happens? What happens is that just like a cocaine addict gets used to seeing that white line of powder, these animals get used to seeing this light every time they get methamphetamine. So now they're associating that bright light with the feel-good of methamphetamine. Okay? It's kind of like when you go to a candy machine and you put in $1 bill and you pull the lever, you are ready to get that candy bar. You're associating watching that candy bar fall down, pulling the lever so that you know you're going to get your sugar, right? Our rats are the same way. Now, we use this paradigm to study sort of aspects of drug seeking, which happens when you're craving a drug. So the analogy would be then, let's say you put your $1 bill in that candy machine and you pulled the knob and it broke. Or worse, it gets stuck and you can see it, but it's not coming down. What do? You shake it, you kick it, you bang on it. Our rats do the same thing. It's impressive, really. So what happens is they keep banging on that lever even if they're not getting methamphetamine. Once they've learned, I'm supposed to get meth when I push here. And this is called cue reactivity. All right, you pulled that knob on that candy machine. It was a cue. I'm supposed to get my candy bar. And when it doesn't have it, I'm reacting to that cue when I didn't get my reward, the candy bar. The rats do the same thing. And what they do, they press. They're mad. They're banging on that lever. So we hypothesized that if we could break the association between that cue and the feel-good of methamphetamine, they won't react so much. They won't care. It's just like if you didn't get your candy bar, you go, I really didn't want it anyway. Right? Well, that's what the rats do when we give them this drug, mirtazapine. It's totally cool. Look at this. Boom. They don't press. They're not so mad. They don't need it so bad. So they don't seek that drug so strongly as they did before. And we think this is going to be very useful in treating cocaine and amphetamine and methamphetamine abuse in humans. And we actually know it works against heroin as well, and our animal models of gambling. How do you like that? We have gambling rats, and that's true. That's another talk. But what's so cool about mirtazapine is it's a drug that does so many different things. So we as pharmacologists want to sort of dissect out the different profiles of these drugs so that maybe we can improve the treatment that we want to give our psychiatrists. And so one of the things that Steve did was he tested this new molecule called SB206553. Repeat after me. No, just kidding. And what this is, it works at a very specific site in the brain. It works at a serotonin 2C subtype receptor. Fancy stuff. All that means is we thought this receptor might be very important in mediating this craving, if you will, this drug seeking. And so what did we do? We gave this SB206553 to these rats, and instead of banging on the lever like they normally did when they didn't get their drug, they went, I don't mind it so much. And if you give a big enough dose, they just walk away. They don't even care. It's amazing. I truly believe we're going to be able to help our psychiatrists with some of these compounds to really, I think, as an adjunct therapy to behavioral cognitive therapy that you already learned about, because we think that they're going to be helper compounds. There will be no magic pill in treating these complex diseases like addiction. But we have good evidence to show that we think we can help improve the craving, the drug seeking, and therefore should help reduce relapse and improve the quality of life. So lastly, what I want to do is talk to you, Dr. Holden mentioned a couple things about non-pharmacological treatments for addiction. And I truly believe that there's a place for this as well. This was a fun study that I was in a couple years ago with some of my clinical colleagues up in Michigan, where we were studying the brains of cocaine-abusing humans. And what we used was a technique called transcranial magnetic stimulation. This is diagrammed here. Basically what it is that the individual sits in a chair and you just set a coil over their head, which is shown here. And it truly looks just like this. And you pass a current through this coil, and as you know, current can generate magnetic fields. And by electromagnetic induction, you actually can change the electrical activity of the brain. And depending on the settings that we use to pass this current and therefore generate this electromagnetic field, we can increase neuronal firing or decrease neuronal firing. Pretty cool. And you already saw a video from Anna Rose Childers showing that this cortex is hyperactive when an individual is craving cocaine. Well, we know we can put an individual with this transcranial magnetic stimulation, with repeated treatments of these, show them these cocaine videos, and you reduce that hyperactivity. It's fantastic. And I love this because it's non-invasive, and these kinds of therapies might be really useful for people where we don't want to give them drugs. Say, for example, a pregnant woman who has a proclivity to abuse drugs, and we want her to stop. This might be a very wonderful way that we can help her and her newborn, unborn baby to be drug-free. So in closing, I just want to tell you guys, it's going to happen. And thanks to you who pay your taxes and lets us get grants from the National Institutes of Health, it's going to happen. So neuroscience has provided a clear understanding of addiction, that it is a chronic relapsing brain disorder, but we understand the neuroscience of each of these processes. We'll be able to intercede here, I do believe. I think therapy should attempt to reduce the drug's rewarding effects, which we talked about a little bit, certainly to block drug-associated conditioned learning, which has to do with cues, drug seeking and craving, and which we didn't talk on today, but we certainly can afterwards if you want to, is to engage cognitive and motivational control in treatment to help boost cognitive and behavioral therapy. So I think in closing, improving treatment should help improve the lives of those who suffer from addiction and should also reduce the stigma that's often associated with drug and alcohol abuse because it is a biological disorder. There should be no stigma. So thanks for your concentration. I appreciate it. Thanks. Oh, we have to go up there. That's right. I totally forgot.
My biggest job tonight as moderator is to remember to repeat the questions from the audience that you may have for the panel, since we're being videotaped tonight. I'm curious about you talked a lot about substances of abuse, heroin and cocaine, and just to the panel, for cannabis in the United States, a number of states are now decriminalizing or legalizing its use. I was wondering if you could opine on the potential impact that may have on cannabis addictions.
Well, I can talk a little bit if you want. Can you? All right, I'm going to try again. Oh. All right, one more time. Is that better? Okay. So I think a couple things are very relevant in this discussion, and I think that I personally would like to see policy to be based more on neuroscience than on some sort of emotional hype that I feel like our culture is involved in right now. In terms of the addictive liability, if you will, of the active ingredients of marijuana, it's certainly not more addictive than alcohol or nicotine, so that's not the point here. The point here is, I think, a couple things. One is, are you using this medically? Are you using it recreationally as an adult? Maybe you're having a toke once a month. Or have we made it such that adolescents have a greater is it more accessible to our adolescents, which we know is incredibly detrimental to the way the brain is developing and to cognitive function in these individuals and can have long-lasting effects. I do think that there is a place for this in our medical community. I think that we're doing treatment a disservice by saying the only way you can get it is to smoke it or these goofy brownies or whatever. I mean, we should be able to dispense it in pills in known doses. So I think part of the problem is this cultural hype about this drug. It is not totally safe, but it's not totally evil. But I'd like for us to approach it more from a neuroscience viewpoint and see if we can't exploit the advantages of these drugs while trying to avoid some of the really harmful consequences that can occur if marijuana, pot, or THC is abused.
Thank you. And if there are questions from the audience, please just raise your hand. Yes?
Dr. Holden, I have a question about, you mentioned that methadone treatment is usually average of a year, that they stay on for average of a year. I work for a methadone clinic, and most of our patients are 3 to 5 years. And I know it's supposed to be a maintenance reduction, but is there statistics that show that they are like a year? Because I'd like to bring it back,
So just repeating for the cameras, your question was that there was a statement about the average length duration of use of methadone is about a year, and you were wondering about the statistics that may support that statement.
I don't know what the average is in terms of if you add up everyone, and that's your numerator, or the length of time everyone is in treatment, and then divide by the number of people, and that would give you an average. What I am almost positive about is that, there might be some exceptions from facility to facility, but the majority of people who go on methadone maintenance treatment are on it for much less than a year. That there's a very high dropout rate, so that it's not. If I said that it was an average of a year, I misspoke. But just the average. One of the big predictors of success for methadone treatment is length of treatment. The longer the person is in treatment for, their better chance of success. But the majority of people aren't ever on it for a year. Is that what you? Do you see a high dropout rate kind of early on, or?
Yeah, no, it's that, actually, I see a longevity with our clients. There's people that have been there 8-9 years, unfortunately. Because it's really not supposed to be a long-term, life-term, they want to wean them, but what happens is they break off, they come back, they break off, they come back. They're not a consistent.
So again, the comment was that you've seen them more chronically on methadone treatment for 8 or 9 years, and that made me wonder if these differences in duration may be due to relapses in the disease itself. Right. Any thoughts or comments on?
I got your point, Doctor.
Yeah, I can go on and on, but I will, just because I think it's a really important fact, is that the people wonder what is the length of time that people should be on methadone maintenance for. And basically it's as long as is clinically necessary. Recovery from addiction, it can take a really long time, sometimes close to a lifetime, for real changes to occur. And even after changes have occurred, people are medically stable, psychiatrically stable, legally stable, and so forth. Coming off of methadone should ideally happen after all those things, and then maybe not. We looked at when I put up that factoid about the people who were relapsed, who were 15 years clean from heroin, who ultimately relapsed within the next 5 years. I think you could make the case, given how deadly heroin addiction is, that maybe those people should have, if they had been on that maybe all those people should have been on methadone maintenance, or at least that should have been an option available to them.
Yes, I thought Dr. Nager's comments were very good, and found it very interesting about the studies that you've been doing and your colleagues have been doing with regard to methamphetamines in mice. Also, one of the opening comments had to do with the various problems with opioids and methamphetamines. But what is the state, or how do your colleagues research, test, how do they relate to alcoholism? It seems that these days alcoholism has gone by the wayside a bit in favor of other more popular drug-related causes.
So if I can just restate, the question was really, there was a lot of conversation about opiates and methamphetamine use in preclinical research. How does that relate to alcohol?
Yeah, to alcoholism.
So I'll make a comment, but this is the area of Dr. Lasis too, so I let her speak as well. But the number one abused drug in our culture is alcohol, period. It still is. Nicotine is right there. It still is high. Number 3 is marijuana. So we who do addiction research are very much aware of all of those things. So I think that the National Institutes of Alcoholism and Alcohol Abuse has a very good budget. Their director is Dr. George Koob. You've already heard some of his work. And he has a real appreciation for the need for research in the neuroscience of alcohol and alcohol abuse. And indeed, some of the fields like genetics, alcohol research leads the field. So I don't think you need to worry. We're very much aware of the ravages of alcoholism, and we're very much involved in trying to make sure that we can deal with that substance use disorder as well.
If I can ask, how do your studies, the ones you mentioned there at the end, on rats and methamphetamines, is that translated all into alcohol abuse?
So the question is, I'll just repeat it too, is the work that's done with methamphetamine or cocaine, for example, does it translate in some way, shape, or form to alcohol abuse? And some of it is yes, because again, as you've already heard, there is some common neuronal substrates or transmitters or biochemical events in the brain that are common among all the drugs that are abused. Well, most of them, let's say that. But of course, every drug is distinct, so there are differences as well. But many of the principles of abuse translate between rats and humans, and it translates among the different drugs. It also translates to behavioral addictions, and I mentioned that briefly, like gambling disorders. So there are some commonalities of all of these disorders.
I have a question for all of you. You mentioned that naltrexone is beginning to use in alcoholism to help curb maybe some of the craving. Is there a time period, say, after a person gets sober, that naltrexone will be prescribed? Is it a month, 2 months, 3 months, 4 months? And then once they end that, craving doesn't go away. I mean, fully. So what is the cycle of the prescription or the time period that the naltrexone would be used?
So the question being, in clinical practice, the use of naltrexone for the treatment of alcohol use disorders, what would be the typical course, if there is a typical course of its use, the duration, et cetera?
No one really knows. One of the basic tenets of pharmacotherapeutic drug trials is that everything seems to be concentrated in showing short-term efficacy, doing things on the order of weeks or months and what have you, as opposed to years. So a lot of times the data for long-term is lacking. What I think, and I hate to give anecdotal evidence, but I would imagine my sense is this matches up with treatment guidelines, is that the kind of glib answer is as short as necessary, but early recovery tends to be the most vulnerable period of time. And so the idea of somebody staying on naltrexone, let's say for a year, if they're able to tolerate it and find it helpful, I think that certainly serves a purpose. And then what you can do is you can take you can reassess. Should they, do they want to stay on the medication? Should they do a trial without it? And you also find out over time. I certainly have people that have gone on naltrexone, found it effective, gone off of naltrexone, relapsed, and then we have to reconsider, should this be a longer term treatment? So I think it varies on a case-to-case basis, and I think we'll know more as time goes on.
In follow-up to that, we talk about, addiction is a chronic disease. So when I hear about the medical management, we're always talking short-term, and especially in the advocacy groups and the conversations that are going on, taking medication in order to assist your addiction is considered not being sober. So, but I'm also hearing it from the medical community, that the shortest term of staying on it is what we would like. Well, I don't hear that from someone who's diabetic and taking insulin. There may be alternative strategies that you would be using combined, but the medical treatment is solid, it's effective, and it takes away the cravings. And so the fact that it's costly, it's delivered in reduced instances because only certain physicians can give it, are barriers. They're not adding to treatment in that way. So I just wanted to make a point that our conversation should be more like, how do we manage a chronic disease over a lifetime, as opposed to from relapse to relapse to relapse. That was the question.
We'll acknowledge that as an important statement then. Next. Yes.
We've talked a lot about the pharmacology of the drugs and giving the drugs and going from relapse to relapse. But you haven't talked much, particularly with alcoholism, about the effectiveness of Alcoholics Anonymous and the use of that modality. We talked a little bit about it with the help groups. But what is your experience? I'm kind of sitting here thinking maybe the people that I know that are having difficulty should be taking drugs and not only be doing AA, because I know a handful of people that's all they're doing is AA.
So if I can restate, the question is around, we focused a lot about pharmacotherapy, but what is the comparative effectiveness of pharmacotherapy versus 12-step programs like AA?
Alcoholics Anonymous is, from a research perspective, is tricky because it's outside of healthcare. It's anonymous. It doesn't lend itself to good quality controlled research, which is just inherent in it and is not a knock against it or anything, but it's more just there's a lot we don't know. And you're right. It was part of one slide where I made and I was hurrying and I will not laugh again. Sorry. Everyone else can laugh for me. And I was hurrying to finish, so I didn't really get to talk about it much. So, Alcoholics Anonymous can be enormously effective. The only issue I have with Alcoholics Anonymous is that if it kind of stands opposed to medical treatment, and I think that sometimes comes up. For instance, I think Alcoholics Anonymous can be enormously effective since it works best for people who have severe alcohol use disorders, whereas people who might have a moderate or a mild form of alcohol use disorder might not be well served by going to AA. But it gets really tricky because just about if one of the hallmarks of addiction is, and I hate to use the term, but is denial. If you tell people that AA might only be for people that have a severe alcohol use disorder, then maybe you might tell yourself, well, maybe and you do have a severe disorder, maybe mine's not so bad. Maybe I don't need to go. Maybe I just need to take medication and that's it. And so it's complicated and nuanced.
And maybe it's an individual. The variability between people and how they respond to different treatments would likely, I would imagine, impact that decision of a person to seek either pharmacotherapy or their physician to institute pharmacotherapy versus other behavioral therapies in their treatment. Yes.
First of all, I'd like to say thank you. Thank you so much for your research that you're doing. I teach, and in the past couple of years, I've had four former students die of heroin overdoses. My son is a heroin addict. I was so glad to hear that there's a positive. I teach science, and I'm thinking that science is going to eventually be the answer. As the public, they have walks for breast cancer. They have all kinds of things for other diseases. You never see anything for addiction. What, as a public, can we do?
I'll jump in. Oh, did you want to repeat this? I'm sorry. I'm very anxious to answer this question. The question was, there seems to be advocacy, fundraisers that are very visual for many diseases, breast cancer, diabetes, Alzheimer's, but you don't see this for drugs of abuse or addictions. And this is true, and many of you in the audience know this is a common battle that those of us who are very interested in forwarding the research to help find a cure for addiction find this extraordinarily frustrating. And I've testified before the US Congress, I've testified before the state of Illinois, House of Representatives, and that is a message. Part of it has to do with the stigma. We still have a stigma about addiction. And honestly, what's impressive about our culture, for example, is when HIV/AIDS came to the forefront in the 80s, what happened? You had a group of people who moved that to the front of our culture, and they destigmatized having AIDS. We need to do the same thing for addiction.
I wish we had a Michael J. Fox for addiction like they have for Parkinson's disease. Someone who is willing to step up and say, you know, I've struggled with this. I want to make it my life goal now to raise awareness and raise research for it. As a director for the Center for Compulsive Behavior and Addictions, we are trying to do this at Rush. We are desperately trying to do this. But it's difficult. We don't have grateful patients who are addicts who want to give toward my research, because most of those people who have recovered and move on, this is something that they really don't want to admit. Again, partially, I think, due to the stigma. So I think part of this, the wonderful thing that C2ST is doing, you all coming here, it's going to be on the web. My hope is this is going to help destigmatize addiction. So someday soon, you will see a march for addiction research or a cure. And I'm hoping that we'll be able to do that.
And we're running short on time. And for Dr. Lassick, I would like to just offer an opportunity if you have any other closing comments that you'd like to make before we adjourn.
Yeah, I'd like to actually just expand a little bit about the comment about alcohol abuse, and I think Celeste had some really good points. They're definitely, so we have a whole institute at the National Institutes of Health that's dedicated to studying alcohol abuse, and that's the National Institute on Alcohol Abuse and Alcoholism. And and I'm part of a large community of alcohol researchers, and we are actively working on alcoholism and trying to find new drugs to treat alcoholism and to understand the genetics of alcoholism. So I think there's a lot of work going on. I think part of the thing about alcoholism is you just don't hear about alcohol overdoses in the news. You know, I think because heroin and cocaine, these illicit substances, are very much taboo and associated with like a sort of rock and roll lifestyle. Like, that's sensational news to hear about somebody dying of a heroin overdose. But you don't really hear about all the people that come in and have alcohol poisoning and die of alcohol-related causes, and it's a huge cause of death in this country. But we are working on it, and there is a lot of funding that's coming from the National Institute on Alcohol Abuse and Alcoholism. So
I want to thank very much the speakers for your very insightful and well-prepared presentations tonight. I want to thank DePaul University, the Society for Neuroscience, and C2ST for hosting this event, planning this event. It's a fantastic organization, and I thank you all also for your coming. Thanks.